Okay, so I'm already recording, so we should be good to go here. All right, so let's.
I cannot see him.
You can't see? Oh,
Yes, you are.
turn that off. Now we should be able to see.
Yep.
All right. So this is 537. This is the sequel to 535. In 535, we looked at basic programming concepts. And one of the last things we looked at in 535 was something called an array. We also looked at two-dimensional arrays. In here, we want to focus on something called data structures, which is really kind of giving a name to something we've already been working with. So a data structure is a structure for holding data. Okay, so what does that mean? Well, when we think about our data, we think of it in terms of variables, doing operations on variables, and storing multiple values for later use under a single variable name. Okay, so when we think about what's built into our languages to begin with, we have our primitive types, which can only hold a value. And then we have our object types, which can hold 0 or more values and potentially do more. It's this object type that we're really going to focus on in here. Even though we've already been focusing on it, we've been building these things. So for instance, in the course right before this, your final project was to build a card game. So we built a card game that had a card object. Okay, so we had a card data structure, and a card object held on to a couple of variables, a suit, a value, and then it probably had a function to display itself, that kind of thing. So we held on to multiple pieces of information and multiple abilities under a single variable name. This has been something that we've been striving for since way, way before object-oriented languages. So when we talk about object-oriented languages, that is languages built around objects like this. It's kind of a chicken or the egg thing. This is a data structure, but it's not the definition of data structures because data structures existed before object-oriented languages existed. So, back to our definition of data structures. A structure for holding data. But it goes a little deeper than that. We can say an object is a structure for holding data. So, all the objects in an object-oriented language are structures for holding data, but not all of them are necessarily data structures. Typically, data structures refers to the common tools for solving higher order problems in computer science. And even that's meant to be somewhat ambiguous. What's a higher order problem? We could just say more complex problems. At this point, we're starting to think about how we solve a problem as opposed to just getting it solved. Because now we're intermediate programmers or something along those lines. Okay? So while a card object is a data structure in that it stores a couple of pieces of information and allows us to do some other things, a card would not be considered one of the grand data structures that belongs to computer science or IT. Okay? That doesn't mean it's not a data structure. Historically, let's kind of talk about where data structures came from. So this is the history of this stuff. Historically, we had variables. And what's a variable? Well, it's a named container for holding a single value. That's really the distinguishing factor for a variable. It can hold a single value. But what if we need to hold more than one value? Well, then we have this thing called an array. A named container for holding one or more values of the same type. Okay, so kind of the evolution of these things. Variables existed first. We need to have a named way of holding a value and remembering it later. This goes back to how human beings solve problems. We remember things, we ask questions, and we use repetition. That's how human beings solve problems. So variables certainly fulfill that, but when we need to store more than one value, variables come up short. So that's where we come up with this idea of an array. But now what's the problem with an array? Arrays allow us to hold collections of similar type of same type data. But what's the weakness of arrays?
It keeps all the memory in a row.
Okay, so that certainly is a weakness, is that it's all the memory must be contiguous. It's not very memory efficient. In terms of the problems that arrays solve, what's a weakness of arrays? Maybe a hint along those lines from the previous class when we did fractions. We had 2 assignments in a row. One of them was to represent your fractions as a 2-bucket integer array. Remember that one? Okay. It worked. We were able to represent fractions that way, but why was that a worse way to represent fractions than our fraction object that we created in the following class? What was the weakness of using 2-bucket arrays to represent the numerator and the denominator? Why were they slow? Okay, that's fractions in general.
Oh.
Yeah, fractions in general were slow, not because we did them with arrays. We had to remember that the numerator was in bucket 0 and the denominator was in bucket 1. That's only if we're storing 2 pieces of information. What if we're storing 60 pieces of information? We need to remember what piece of information we stored in bucket 0, what piece of information we stored in bucket 5, what piece of information we stored in bucket 32. We didn't have ways of distinguishing between those values, because an array is just a contiguous chunk of memory where bucket 0 holds one value, bucket 1 holds another value, bucket 2 holds another value, so on and so forth. So a weakness of arrays is if we're going to store multiple pieces of information that mean something, we do not have a way of remembering that built into the structure. That's where objects are kind of nice. We were able to build a fraction object and give it 2 fields, numerator and denominator. Then we can ask that fraction, give me your numerator, give me your denominator. So we had ways of talking to the fraction in such a way that we were able to know what we were working with, instead of having to remember something was at bucket 0, something was at bucket 1. Okay? So we solved the problem using our object-oriented version of, it's fair to call objects data structures, but it doesn't fall in, if you were to get a data structures textbook, you would not find the fraction object as an example in the data structures textbook. We're going to be talking about lots of known data structures like linked lists and stacks and queues and trees in here. But it's still fair to say that our fraction object was a data structure, just like our card object was a data structure. It's just a much more domain-specific data structure as opposed to a generalistic data structure that could be used for solving lots and lots of different problems. So in any case, we needed something better than arrays. Well, before we had object-oriented languages, language like C had a thing called a struct. And a struct, let the programmer define one or more named variables for holding multiple pieces of info. So, for example, in C, we could have created a struct that held two pieces of information, a numerator and a denominator. And we could have said that guy is a fraction. Okay? So this predated object-oriented languages. This is not an array. It's kind of array-like, but it's not an array. It's a structure that we can say holds a num and a denom. So I could say f.num or f.denom and put values in there. Okay? So this predated object-oriented languages, and this was called a struct. Object-oriented languages redefine the concept of a struct into things called objects, into a class. The weakness of structs we did not have the ability to use functions or procedures, which now are called methods. So in non-object-oriented language, functions are methods that return a value, procedures are methods that don't return a value. Object-oriented languages, they're all just called methods. Some have a return type of void. So structs were weak in that they could have places for storing a piece of information, but we didn't have a convenient way of referencing reusable chunks of code, abilities, functions, subroutines, procedures, whatever you want to call them. We sort of kind of had a way of faking it in an old language. Not really important for us, but at the very least, it's fair to say it wasn't convenient. So object-oriented languages allow us to create classes that have fields in them, those are our variable names, as well as methods for doing things. Okay? Now, our data structures are going to benefit from that same sort of thing. Now, if we go back historically, let's talk about our first data structure here. Most of today, we're going to be talking about something called a linked list. This is the base data structure that acts as the starting point for most other data structures. So a data structures textbook would usually refer to the linked list. Well, we refer to most of your data structures as being structures built on a linked data type, a linked list data type, and we'll talk about that today. But this is kind of our most generic data structure. Now, data structures, again, existed before object-oriented languages existed. So back when we just had the C programming language, we would have been able to write linked lists. They existed. We could create a linked list. So it's important to draw that line in the sand between a data structure and an object. Okay? Some objects are data structures, but not all data structures are objects. Okay? Although the line is much more blurry today because we can make almost anything We can call almost anything a data structure if it's a structure for holding data that we're then going to use. But most data structures that we write are very domain specific. We were doing a card game, we wrote a card data structure because it benefited us for the card game. We were writing a fraction homework assignment, so we wrote a fraction data structure because it helped us do fractions. Generic data structures, which linked list is one of them, this is something that is defined. It's built into most languages, but we don't know that because we're going to write them ourselves and then use our own implementation. Why make it easy, right? Okay, so remember that. When you do your homework, you can't use the built-in linked list data structure. We're writing our own. Once we go to trees, I'll let you use linked lists that are built in. Then we'll just use our own trees. Okay?
As usual.
Yeah, how else would it be fun, right?
Yeah, you bet.
All right, so linked list is a generic data structure that allows us to solve a wide array of different types of problems. Sort of kind of pun intended. So we're going to call linked lists as a competitor to arrays. Linked lists allow us to store collections of information. So linked list allows us to store collections of, just so we can make the direct comparison, I'm going to say same type information. So we could have a linked list of strings just like we could have an array of strings. Make sense?
Why? Same type of information.
Yeah, so like this becomes blurry because we can call it similar information because everything can kind of become an object. I just don't want us to make a distinction between linked lists and arrays right now. So we're going to say linked lists and arrays are built for holding a single type of data. So you can build a linked list for holding integers. You can build a linked list for holding strings, a linked list for holding fractions, a linked list for holding cards. Okay? So a linked list is kind of a competitor with arrays. With an array, for instance, in our card game, we created an array of 52 cards built for holding card objects. We could similarly build a linked list for holding cards. So why would we want to do one versus the other? Well, we need to go back and review arrays. So arrays are considered to be very fast. Why are they fast? Because they are represented in contiguous memory. This allows the various, I call them buckets, of the array to be calculated mathematically. So we can jump immediately to bucket 6 or immediately to bucket 9 by using math. As a quick refresher of that, let's say we have a 4-bucket array. Well, 3 buckets is enough. Nice small array. So we have a 3-bucket array, and I'm going to put some data in here. This is a 2, a 5, and a -1. That's the values that are stored in there. And we're going to say our array, the name is AR. And the way we would have built this array, since I'm holding integers here, is I would have said int array AR is equal to a new int array 3. And then I would have said AR at bucket 0 is equal to 2, AR at bucket 1 is equal to 5, AR at bucket 2 is equal to -1. Okay, so this code would have generated this thing. And the value of AR would be a memory address. Why? Because the new keyword was used to create it. Okay? So AR's value was whatever the new keyword produced, which is the memory address, which points into memory where the actual values, those three values of an array are. Okay? So what ultimately got created here was this type of thing. Now, what does that mean? This is bucket 0, this is bucket 1, this is bucket 2 in our array. Similarly, I'm going to put some memory addresses above here. This is memory address 100, 104, 108. Okay? So, the fact that AR holds a memory address 100, that is said to point into memory at memory address 100 where bucket 0 of our array AR lives, which currently holds a 2. And what we mean by arrays, the buckets of them being able to be calculated, we know that bucket 0 is at memory address 100. We know that bucket 1 is at memory address 104. We know that bucket 2 is at memory address 108. Does that make sense? We know all those things. Now, how does that work? It's calculated because if I say AR at bucket 0, that's the same thing as saying go to AR, add to it 0 times size of integer. AR is 100 plus 0 times 32. Well, actually, it's called 4 bytes. 32 bits, 4 bytes. So 0 times 4 is 0. So that means AR at bucket 0 is at memory address 100. Bucket 0, memory address 100. What about bucket 1? Bucket 1, AR at bucket 1, is AR plus 1 times size of int, which is memory address 104. Again, an integer in Java is 32 bits or 4 bytes. A byte is 8 bits. Okay? And similarly, if we did 2, it would come out to 108. Okay? So we can calculate these individual buckets. We don't need to traverse it. We don't need to start off at bucket 0, then walk to bucket 1, then walk to bucket 2 in order to get to bucket 2. We can go directly to bucket 2. That make sense? Okay. That's what's nice about arrays, is that they're fast. Fast, because we can mathematically calculate them. But they're memory inefficient. Why? All the memory must be contiguous. That means in a row. So if I'm going to store, in this case, a 3-bucket integer array, that means I need, what, 96? 96 bytes in a row. I'm sorry, 96 bits in a row. 12 bytes in a row. So this 3-bucket array took up the memory between 100 and 108. So really 100 all the way up to 112. All that's being taken, it's being used. Okay? Whether we put something in there or not. This first line of code here, integer array AR equals new integer array 3. Remember, this guy is creating an empty array. It's grabbing all this memory. It's giving us the indexes, but it doesn't necessarily put any values in there. It'll be default values, but we never rely on that. So that's why these next 3 lines I went ahead and actually placed values in the array. Okay? So arrays are super fast because we can calculate the positions, but they're memory inefficient. Most of the time, probably not that big of a deal. But keep in mind that historically, this was a big deal. Memory wasn't always in abundance as it is today. So there was a point in time where just saying that arrays were memory inefficient meant something very, very terrible. Today, most of us have 4, 8, 12, 16 gigabytes of RAM in our computer, you got to get to a pretty big array before that really starts becoming a problem. Okay? But we're going to talk about another problem with arrays in here. All right, so in order to talk about that, let me go ahead and let's open up Eclipse. Let's look at some code examples. I assume you've been practicing your programming every week?
Yeah. I actually got 2 more classes on programming, on Java Oracle programming. Still taking those classes.
So we're going to create a new project. We'll call this 537.
Class is pretty easy. I mean,
Which?
Just all, I mean, whatever I'm taking from Oracle.
Oh, SQL? Or you're writing Java stuff?
Yeah, and they're like all built up. It's like
Is it here?
Alice, yeah, an MBA.
Oh, in the MBA program.
Yeah.
Okay. Well, it's not a programming class then. It's a database
Yeah,
management
just-
class, and you're using SQL to query it.
Yes.
I got it.
Yeah. It's not.
Okay, CSC537, spring 2014. That's the year it is, right?
Yeah.
Telling you, I'm losing it. Wait, hold on. See, I'm not even the right thing. Let's cancel this. Let's try this again. New Java project. There we go. Okay. Then we'll come in here, we'll go ahead and create our driver class. And we'll make this do our basic hello world program just to make sure everything's firing in all cylinders. Oh, just so you know, I'll have the syllabus up sometime tomorrow morning probably. It's the same grading structure I always use. Your first 2 homework assignments are up currently. I'll unlock the class when we talk about the end of class. I didn't pre-populate Angel because I was playing video games. Well, Diablo 3 expansion releases tomorrow. I have to be ready.
It's a big.
Well, it's actually mid 12:01 tonight.
It's huge event.
Do you play that game?
No, I just stopped.
So you're just making fun of me now. I get it. Makes sense. Make a little note in your grade there. All right. So here, we'll just do a quick system out to println hello world. Quick rule of thumb here. You never know when I'll throw a quiz at you. Everybody in here should be able to write this program off the top of their head. Okay? So if I were to show up one day and say, take out a piece of paper and have you write a generic hello world program with no errors in it, I said your entire grade is dependent on this one thing, everybody should feel relieved that, oh, free A. Okay?
Nice. For the people who don't bring paper.
Don't bring paper. You can always borrow paper or buy paper off your neighbor. It's a supply and demand type thing. It's a bartering option, a bartering opportunity. That's right. It's a capitalist society. You're Uzbekistan, right?
Yeah, it used to be Soviet Union. It's done.
Aren't they taking it back now?
No, it's a.
Oh, it's
Crimea.
Ukraine.
Crimea,
What?
yeah.
Yeah. Oh, it's all the same crap.
They mobilized everywhere. Right.
Oh, did you see in the news they finally found the plane?
Yeah.
That
This morning.
yeah, with the. How does it take a month to find a plane?
21st century.
Yeah, and it wasn't even good news. I guess
Yeah.
it crashed.
Yep.
So nah.
No.
But imagine these family members have been sitting there worrying about this for a month, waiting to get the result. It's terrible. Okay, so here's our basic hello world program. Blah, blah, blah. Now, what we want to do here is we're going to go ahead and create an integer array. And we're going to go ahead and make it a 10 bucket integer array.
Okay.
So we're going to store 10 things in this. Right now it's empty, completely empty. Now I want to go ahead and fill it up with some random numbers. So we're going to create an instance of our random object. and that's going to want us to import java.util. All right. Now I'm going to go ahead and fill it up with random numbers between 1 and 10, whatever. Okay, so for int I is equal to 0, I is less than ar dot length, I plus plus. And we're going to say ar at bucket I is equal to r dot next int 10. That'll give us numbers between 0 and 9. Good enough for the example I'm writing here. So if I go ahead and print that out real quick. So this first for loop fills it up with some random numbers. The second one prints them all out. So I should see 10 numbers between 0 and 9 spit out to the screen. Okay? Good enough. All right. Now, here's a problem with arrays. So it's kind of slow. Is that a ringtone?
It's a computer.
Oh, somebody's computer booting now?
It's like a Windows, like a wrong thing happens.
Oh, I see.
Like that now.
So I like the upbeat ringtones. We always get a couple of those in the grad classes. Okay, so arrays, they are always good because they're fast. Biggest benefit of arrays, super, super, super fast. They're memory inefficient, but who cares? By today's standards, right? So now we're looking for our other problem. The big problem. What's the big problem? Well, this is the big problem. You know when I originally built this, I decided I wanted to hold 10 numbers, but now I want to hold 12. How do I add 2 more numbers to this array?
You don't.
Change that.
Let me write a couple of generic methods here. So I'm going to create a method. This guy's going to be called print array. It's going to take an integer array, blah as a parameter. And it's just going to print out the contents of that array. Okay, so I made this as a generic method, so I should be able to pass any integer array to it, and it should be able to spit out the contents of it. Now I no longer need this second for loop. Instead, I can just say driver dot print array AR, and it should print out the contents of AR. Okay? Now, after that line, I decide, you know what? I really need AR to hold an extra couple of values. But now, I've changed my mind after I've already filled it up with some stuff. I still want all the old stuff. I just need 2 more values in there. So I need AR to ultimately hold 12 values. I want to keep all the values that are currently there, but I want it to hold 2 additional values. And I want those 2 additional values to be random numbers between 0 and 25. For no good reason. Okay? How would I do that? How big is my new array going to be? It's going to be 12, right? 2 bigger than my old one. So I'm going to say int array temp is equal to new int array ar.length plus 2. 2 elements larger than my original array, right? All right. Then I'm going to go through, I'm going to say for int I equals 0, I is less than ar.length I plus plus. Now we know that temp is 2 buckets longer than AR, correct? The end of 535, we were talking about parallel arrays, where we had 2 arrays that are related to each other in some way. Okay, so I know that if AR looks like this, we know temp looks like this. It's 2 buckets longer, right? Okay, so we know if we spin through every bucket of AR that there will at least be corresponding buckets in temp. And then there'll be a couple of extra buckets at the end. Okay? So I'm going to go through all the elements of AR. I'm going to set temp at bucket I equal to AR at bucket I. Okay? Then what I'm going to do is I'm going to say driver dot print array temp. So the first thing it's going to print is AR. And here I'll just do a quick system.out.println. That's our dividing line between our 2 print statements. So we'll print one array that have a bunch of asterisks, then we're going to print the other array. So the second array I'm printing is temp after I've copied all the contents of AR into temp. And what we're going to see is we're going to see temp has all the original contents of AR in it, and then it's going to have 2 zeros at the end. 2 buckets we haven't actually put real values into. It's the default value. Okay, so there's the original AR. Here's temp, all the original stuff with 2 zeros at the end because it has 2 extra elements in it. Make sense? And then what did I say I want those elements to be? I want them to be 0 to 25 or 0 to 24, whatever. So we're going to go ahead and we're going to say temp at bucket, just for the sake of whatever here. I'll just hard code in the buckets. Temp at bucket 10 is equal to r dot next int 25. That'll be 0 to 24. And then temp at bucket 11. If it's a 12 bucket array, legal buckets are 0 to 11. Okay? So temp at bucket 11 will be a random number between 0 and 24. Go ahead and run this again. We should have our random numbers there at the bottom. We got a 3 and a 5 out of it, which isn't all that interesting, but there, we got a bigger number. There's a 24. Okay? Now, what did we just do? If we were to graphically depict this, we have a nice house, right? And we decide, you know what? We actually need one more bedroom on this house. So what do? We take this house, we build another house, the other house had one more little bedroom on it, like that. We copied everything into this new house from the old house, and then destroyed the old house. How efficient is that? Is that how we would do things in real life?
We just add up one.
We just add another. We add an extra little room onto the house, right? We wouldn't build a brand new house with one extra room, move all of our crap over to it, then literally blow up the original house. That makes no sense, right? Okay. The biggest problem with arrays is they are not mutable. Mutable is a fancy computer science word for changeable. Changeable, all right? That's what not mutable is. It means that we cannot change the structure. We can change the values inside of it. We can change the bucket 5 to be a new value, but we can't add on additional buckets. We can't change the structure, which is problematic. So if we decide we need to hold one more piece of information, well, then we need to build a brand new array. Now let's think about some real life problems. A real life problem related to this would be, let's say you're at a doctor's office and the doctor has a collection of patient records. Okay? So let's say these patient records, just to keep it simple, we have a patient object. Patient object has first name, last name, phone, email. 4 pieces of information. Okay? Now, how many patients is that doctor going to have on the very first day? Maybe they have a couple or something like that, but far less patients than they hopefully will have at the end of year 3. Correct? So, if you are writing a piece of software for this doctor to store all the patients, how many patients are you going to allow them to store?
Like in a year?
Well,
Be
okay,
to point
sure.
out that if you make a list of it, eventually you're either gonna have too much, and you're gonna have leftover. You're not gonna have enough.
Yeah,
And
so
can't change it.
you can decide I'm going to go ahead and give them enough room for 1,000 patients and potentially waste a lot of space forever, right? Maybe they never get 1,000 patients, but you're wasting all that memory. Or you could say, okay, we're going to give you enough for 10 patients. Well, is there a pretty good chance they'll have more than 10 patients? Sure. So what are they going to do? Well, we're going to have to destroy all the old patient records after we copy them into a new filing cabinet that can hold more patient records and then add the new patient records. So we have to make this decision up front. If every single time we got a new patient, we had to literally rebuild our storage container to hold our patients, that would be pretty inefficient, right? Now, the real question here is, what if let's actually kind of write this. I'm going to create a class here. Let's call this guy elastic array. Okay? We'll call him an elastic array. And our elastic array is going to control a private integer array internally. We'll call it AR. Okay? And we'll have our constructor, public elastic array. And this guy's going to take no parameters. And we're going to say AR is equal to new integer array 0. Because there's literally nothing in there. Right? All right. Then we're going to write a little method, public. Let's write a couple of methods. Let's write a public get array. Oh, we don't need to get it. Let's just teach it how to display itself. And we're going to just do system.out.println AR. And this method is a void method, returns nothing. Okay? So here's the beginnings of our elastic array. It's going to control a private field of type integer array. The constructor is going to be called elastic array. It's going to start off our array as being literally an array with no buckets, empty array. I don't know why you'd ever do this, but this is how we're going to write our elastic array. Okay? And then we're going to teach elastic arrays how to display themselves. Let's go ahead and create an instance of our elastic array out here. So we create our instance of elastic array, then told that array to display itself. Now notice that displaying our elastic array is different than saying system.out.println EA. If I display EA, that's going in, it's going to print out the memory address associated with the array. If I print out EA, what's that going to show? The memory address associated with this variable name. Okay, so these should both be memory addresses, but one will be an integer array memory address, this guy. The other one will be an elastic array memory address. Make sense? Okay, so the first one prints the pointer that is our internal array. The second one prints the pointer that is this guy. All right, now, by elastic array, we mean we want to be able to keep adding things to our array, no harm, no foul. So we're going to create an add method that takes in an integer. That is an integer we want to add to our elastic array. Okay? Now, in order to add something to our elastic array, let's assume this is the first integer we're adding. How many current values are in our elastic array? Let's write a length method for our elastic array. And this guy should return the number of elements that our elastic array can hold. So it's going to return ar.length, which right after this guy's been built, if I print out ea.length, what should this print out? I built my elastic array right here. That's what the constructor does. How many elements does this array hold? 0. So it's going to print out this guy has a length of 0. All right, so that's the current length of my elastic array. Now, if I add a value to my elastic array, what does that mean? Well, we already proved that we cannot add values to an array. We need to build a brand new array, copy all the old crap over, then add our new value, right? Okay, so we're going to say int array temp is equal to a new int array. How big is this guy going to be? It's going to be ar.length plus 1. 1 bigger than it used to be. That way we have room to put our new value. Then what are we going to do? We're going to spin through and fill up our elastic array. Fill up temp with all the values that are in AR. Then copy in our new value. So for int I is equal to 0, I is less than ar.length, I plus plus. We'll say temp at bucket I is equal to AR at bucket I. Pretty much the same thing we did before. Then we'll say temp at bucket temp dot length minus 1 is equal to val. Make sense? So create a brand new array temp that's 1 bigger than my old array. Then fill up temp with all the elements that are in the original array. Then add my 1 extra value into temp. Finally, AR is equal to temp. Overwrite the value of AR, which is a pointer, with the memory address that temp holds. Okay? What did we just do there? We did the equivalent of this. Just for the time being, let's assume AR had 2 values in it. So we're going to say AR points here. And let's just use memory address 100 again. It's a nice friendly number for memory addresses. So this is bucket 0, this is bucket 1, and we can put some values in there. This is 100, and this is 104. That's what AR currently looks like. But now we are calling, and all this stuff here is housed inside of our object called elastic array. So this is like what's under the hood of elastic array. Make sense? Okay. Now, when we add a value to our elastic array, when we call this method right here, this add method, the very first thing we did is we created a brand new array that's one bigger than our old one. So I'm going to do that. Just going to copy all that. We'll drag it down here. This guy is called temp. We'll put this guy at 500, just different place, right? This is 500, 504. And he has one more bucket. Than the previous guy. Okay, so right here we say create a new variable named temp of type integer array, and this guy is going to be a new integer array capable of holding as many elements there is in AR plus 1. And that creates this for us. That is a brand new array somewhere else in memory. I'm just using simple memory addresses, but somewhere that's not at memory address 100. So I put this guy at 500 with enough space to hold one more thing than this guy used to be able to hold. This guy could hold 2, this guy can now hold 3. All right, but nothing's currently in there. Next, what do? We spin through copying everything from AR into temp. So that loop right there that I have highlighted, that's going to go through and it's going to put into bucket 0 of temp, whatever's at bucket 0 of AR. Bucket 1 of temp, whatever's at bucket 1 of AR. So we copied all the elements from AR into temp. Does that make sense? Then what do? We put our new value, let's just say this guy was a 13. That is this guy. Whatever was passed into that method, we're going to go ahead and put that in the last legal bucket of temp. Temp.length minus 1. Arrays are 0 indexed. So if it's a 10 bucket array, legal indexes are 0 to 9. Length minus 1. All right, so that's where we put in this very last guy. Now, the last line is the magic part, the part that we need to really, really, really understand for this class. Okay? Which is kind of just backing up for a second. If you remember when you took the 535 class, some people in here literally had the 535 class last week. Some of you had the 535 class a semester ago or even longer. But if you remember back from that class, something I said probably about halfway through the course is we talked about how most textbooks say that pointers don't exist in Java, right? But we see memory addresses all over the place, so pointers clearly exist in Java. Data structures is all about pointers. It'll make sense here in a few minutes, but we really need to understand pointers in here. All right, so everything up to here, this is where we put that last value in. We still have 2 separate arrays. Now this last line is the magic. What do? I set AR equal to temp. AR is a variable that holds a value. What value does it hold? It holds a memory address. Temp is a variable that holds a value. What value does it hold? It holds a memory address. That is to say, AR's value is 100. Temp's value is 500. We are saying in this line right here, AR gets the value of temp. So if temp's value is 500, what we did is we just set AR's value to 500, which effectively made AR point to the same place temp points to. That is, we abandoned this array in memory.
Whatever comes next, they'll just...
So this guy is now marked for garbage collection. Java has something called automatic garbage collection. little dump truck that walks through memory, and whenever it has something that's available to be cleaned up, it cleans it up. How do we know this guy's available? Well, when he's still pointed up here, this memory address, well, let's switch it back to 100. 100 had a memory count of 1. So let me actually, we'll put pointer counts in here. So the pointer count for memory address 100 is 1. The pointer count for memory address 500 is 1. As soon as we change the value here to make this guy point here, pointer count went up to 2 for 500. Pointer count went down to 0 for 100. That makes sense? As soon as the pointer count goes to 0, what does that tell the Java virtual machine? It says there currently are 0 objects that point to this guy. Therefore, you can erase him from memory. That makes sense? So as soon as we hit that last line here, what we've essentially done is we've abandoned AR. Everything that AR used to be, we've gotten rid of. Does that make sense? And we'll prove that here. Now, notice at this point, we're not displaying the contents of our array at all, of our elastic array. What are we doing? We're just displaying the memory address, correct? Of the internal array. So if I create, well, that's kind of like elevator music. So if I create my array, my elastic array here, and then I print it out, this is going to show me the memory address, right? Should be the integer array. All right. Now, if I say EA, that's fine. Let's just do EA.add 13. Now we know the length used to be 0. Now the length should be 1, right? And then we say EA.display. We should see a new memory address now. 2 different memory addresses, right? After we added it, what happened? We created a brand new array, filled it up with all the old crap, added our one new thing, and then set our internal array to point to the new guy. And then the next time we call display, the memory address for AR is different. What if I do this again? We'll add an 8. Tell it to display. We'll get another memory address. That makes sense? Now, every single time I display, if I also then do a system.out.println ea.length, we'll see that the length of our elastic array keeps getting longer. It goes from a 0 to a 1 to a 2. 0, 1, 2. It's really got real values in there. We should be able to see this. Let's update our display method. We've already seen that the memory address keeps changing, right? So now we're going to update our display method. Instead of printing out the memory address, we're going to go ahead and we're going to just do a quick system.out.println. Let's just put some asterisks in here. And then we'll write a loop that goes through. For int I equals 0, I is less than AR.length. However long AR is right now, right? Each time AR keeps getting longer every time we add a value. So the first time we try to call this, AR length might be 0. It might be 1, then it might be 2. I++. And just for the sake of sanity here, I'm going to, when I print this, I'm going to print out one character at a time all in one line instead of a big long thing here. So we're going to say print AR at bucket I concatenated with a space. We'll just have them all separated by spaces. And then after that loop, we'll kick it down the line. So if my array currently holds 1, 2, 3, it should print 1, 2, 3, then kick it down the line rather than 1, 2, 3. Just for aesthetics. Okay? So, we no longer need to print out the lengths here. So here's my elastic array. I'll tell it to display itself. We should see the asterisks, but no content. There's no values in it initially, right? Then I added a 13. Tell it to display itself. We should see the asterisks. Then we should see a 13. One value in there. Then we added an 8. We should see the asterisks, 13 space 8. Make sense? So we're clearly adding things on here. Does that make sense? All right. Let's go ahead and give ourselves our random object again to generate some random numbers. Now let's generate 20 random numbers and add them to our elastic array. So we're going to say ea.add r.nextInt, and let's just do numbers between 0 and 9. Okay? We create a brand new elastic array, and we created a brand new random object. We're going to spin through, we're going to generate 20 random numbers. And each number we generate is going to be a number between 0 and 9. We're going to add it to our elastic array. Afterwards, we're going to say ea dot, oh, hello. Display, which should show our 20 random numbers. You're good? No harm, no foul? Now, just looking at the output, everything looks fine. Even if we look at driver here, it's pretty clean, right? No big deal. Adding stuff to our list, no big deal. Even we look at elastic array, no big deal, except the amount of destruction that occurs in this one little method here is ridiculous. I'm just going to print out a little statement here. System.out.println. Every time that add method gets called, we are literally abandoning old memory. I run this again. We burned down 20 houses so we could store 20 random numbers. Question is this wrong? Worked?
It's like, I know, it's like you said first time, like it's like still killing, like destroying the houses and building another house.
Okay, but it worked. I mean, what if we did this 1,000 times? How much total space did we just take up to store 1,000? Well, the last time through we need to store 1,000 numbers, right? Time before that we had to store 999 numbers. Time before that we had to store 998 numbers.
Every time.
Well, how much memory is 1,000 numbers? Here's the math real quick. I just won't display it. Int sum, we'll start off at 0. For int I is equal to 0, I is less than 1,000, I plus plus. That's the number of bytes each time through. We're going to say sum is equal to sum plus I times 4. So the first time sum will be equal 0 times 4, 0. Next time it'll be 1 times 4, 4, and 8, 12. So sum will sum up the total number of bytes that we had to take up to store our 1,000 random numbers. That's bytes. Okay. I'm going to go ahead just so our math is easy. I'm going to change this to a double. So I'm going to do some division here in a second. So again, it's in bytes. If I want to go from bytes to kilobytes, I divide by 1,024, right? What if I want to go to megabytes? Now, to put this into perspective, to store 1,000 random numbers, so 1,000 integers, should have taken 4,000 bytes total, correct? 4,000 divided by 1,024 divided by 1,024 is 0.0038 megabytes. Make sense? The way we've written it at this point, the level of inefficiency we've used, the amount of memory we just used is greater than would have fit on a 3.5-inch floppy disk a decade ago. Those disks held 1.44 megabytes. Modern day terms, we can say that the amount of space we just took up to store 1,000 random integers is about the same amount of space as it takes to store an MP3-ish.
Yeah.
MP3 is a little bit bigger than that, but ish. That was pretty wasteful.
1,000 random numbers.
There's tiny little integers, right? But this is for a simple little tiny problem, right? We can see how this can scale. What if I did this for 10,000? Now I'm at 190 megabytes. 100,000? I'm at 20,000 megabytes. $18.6 gigabytes to store 100,000 integers. Now you might notice that I'm not actually storing 100,000. I'm just doing the math down here. I don't want the Java virtual machine to die. Actually, let me go ahead and let's make it 100,000. That should sufficiently kill it.
Want to stop you first?
I will in a second. Hold on. Oh, that's actually quite interesting. It did not crash. Why? Automatic garbage collection kept up. I didn't expect that to happen. I thought it would outpace it. We literally just used 18.5 gigabytes of memory. My computer doesn't have 18.5 gigabytes of memory in it. I have 16 gigabytes of memory, which is a lot. It's in a laptop. I just used more memory than is in my laptop with a 20-line program. Very memory inefficient, right? Now, what's interesting here, going back to automatic garbage collection, this guy. Automatic garbage collection is something that is almost always available nowadays on our desktop computers, laptops, desktops, but initially it was not available on our mobile devices, like an iPhone. Now they've put them on iPhone. Now why wouldn't, and also Android devices, why wouldn't it been enabled on our mobile devices? Well, mobile devices are running off a battery, correct? So if it's running off a battery and we have this extra little guy, this dump truck that's driving around memory, cleaning, just constantly looking for memory that's not being used to clean up, that's going to take up battery life, right? Because that's another program that's constantly running. And when we're on our mobile device, battery life is supreme, correct? We really care about battery life. So we could write an iPhone program in just a couple of lines of code that literally will just burn through all of your system's memory. You could probably write a program for Android, so kind of talking about from a virus perspective. Because Android, the Google Play Store does not, there's kind of two different philosophies in how they check apps. If you upload an app to the Apple Store, there's about a 1 week period where they test it and check it and all this other stuff before they actually release it on the App Store. Android, you can just put it out there today, and only when somebody complains about it, if there's something wrong, do they yank it from the store. So it would be easiest to pull this off on Android. We could write a program in Java, because Android development is in Java, so we just wrote it. That would literally run a phone, either A, out of memory, but maybe garbage collection keeps up, but we would definitely have it sitting there dying battery life in order to keep the automatic garbage collection working. You could probably drop an Android device's battery life down to about 10 minutes by writing one stupid little app like this. So kind of an interesting little concept there, if you will. It's actually very entertaining to me that automatic garbage collection's kept up there. It would not have in many circumstances. Could be that, this is a quad-core processor, but even then, I'm very surprised it kept up. Okay. So back to arrays, even though they're memory inefficient in general, the fact that they're not changeable, adding stuff to them is highly destructive, which then puts this memory inefficiency on steroids. So this kind of comes full circle to what we talked about right at the beginning of class today. Memory inefficiency isn't that big of a deal to us today because we have so much memory. But we just wrote a small little program that wasted almost 17 gigabytes of memory. Right? Now, that's a small program. We don't all have 17 gigabytes of memory in our computer. We can pretty quickly outgrow what we view as being an abundance of memory, which is a stupid little programming mistake, something like that, right? So this concept of not being mutable, along with it being innately memory inefficient, allows us, kind of prohibits us This prohibits the storage of an arbitrary amount of data. That's kind of what we've written here in our little program. We created this thing called an elastic array, elastic meaning it just keeps growing, and every single time we add something to it, we're creating an arbitrarily larger array, correct? And it seems to work fine. The ultimate end result is this is perfect. I can hold as much crap as I want. And at any point in time, I'm not actually using up any more system memory than the total number of elements being held times, in this case they're integers, times 4 bytes. It's not so bad. But the amount of overhead that's going into that doesn't make it seem all that desirable. Maybe not the end of the world. Still worked. Probably would continue to work. But we can certainly at least see the problem. Make sense? So that's where linked lists come in. So in our example over here, we were holding 2 elements, a 2 and a 5, right? I'm actually going to just steal that one real quick. A linked list has one variable called head, and head always points to the front of the list. This will make sense here in a second. We're going to kind of describe what a linked list is by looking at an example. Each element of a linked list is typically stored inside something called a node. We'll talk about them in a second as well. Okay, so if this is the array version of a 2-bucket array, this is the linked list version of a 2-element list. We have head, which points to the first element. That element has a pointer that points to the next element. This element has a pointer which points to the next element, and this guy points to nothing, so we know that's the end of the list. Now going back here, when we talked about arrays, we said arrays were fast because we can, since they're represented in contiguous memory, this allows the various buckets to be calculated mathematically. We can just jump to bucket 0, to bucket 1, to bucket 2. Linked lists are not contiguous in memory. Let's say that this guy is at memory address 100. Let's say that this guy is at memory address 374. Okay? These 2 elements, the 2 and the 5, do not sit right next to each other in memory. They sit somewhere in memory, and then they control a pointer that points to the next guy. So in a linked list, we have something called a node. A node object would be how we would call it in an object-oriented language. We call it a node object. A node object is going to have, let's just say we're storing a bunch of integers, which is what we'll be doing today, and that's what you'll be doing for your homework assignment. It's going to have an integer, and this guy's usually called payload. When we think about our node, what we want to think about is this is the container which actually holds the value at a particular bucket in our linked list. The payload is that value. Now, besides holding a value, a node must also keep track of another node. That is the next node, the node that this guy points to. Okay? So back in this picture, this guy's a node. This guy's a node. This node's payload is 2. This guy's next node holds the address 374. The address where this other node lives. Okay? So, if we were going to come in here, create a new class, call this guy node, private int payload, private node, next node. So every node knows about the value it holds, and it knows who comes after him in the list. This is something that's called a singly linked list. We'll also talk about a doubly linked list next class, but for right now we're just talking about one direction. Start at the front, go towards the end. Okay, private node, next node. Now we have our constructor for our node, public node. This guy's going to take in a value, int payload. We'll set this dot payload equal to whatever payload you passed in. So when we create a new node, if I come out here to driver real quick, let's get rid of our elastic array stuff. I can create a node n. This guy's a new node. Let's say it's the value 5. Is that what I had in my picture? No, 2. We make it the value 2. Okay. That's going to create a brand new object, node, whose payload is 2. And as of right now, we want it to look like that. So we're going to have a single node whose payload is 2 and whose next node is nothing. Okay, because he doesn't currently have a next node. He doesn't point anywhere. So inside the constructor for node, we're going to set the payload to whatever the payload was passed in. And we're going to set this dot next node equal to null. It currently points nowhere. Okay? Now, we want to create a couple of accessor methods. We want to create a get next node. We also want to create a set next node. We should be able to tell this guy who his next node is, because eventually we're going to be using those things together, correct? Okay, so we're going to kind of let this grow like a plant as we start doing this. So right now, we're not going to give any new abilities to a node, because now we need to think about how do nodes fit inside the ecosystem that is a linked list. This whole thing we have here is inside of one giant bubble called a linked list. What's a linked list? It has a pointer that points to the very first element of the list. So we have a node head. So we're going to go ahead. We're going to create our linked list object. Now, I'll mention this again just in case you get any sort of weird behavior when you're working on your homework. There already exists a linked list object in Java that lives in java.util. You are not allowed to use that. By creating a more local definition of linked list, you should not have any problems. But if you ever get it yelling at you, underlining something in red saying you must import java.util, know that you've done something wrong in your code. Probably named linked list something different or something like that in the code, because that's what it's thinking you want to use the one that's built in. We're not allowed to use the one that's built in. If it would make you feel better, we can call this guy LL or something like that, but I'm going to call it linked list because there's nothing wrong with doing that. And inside linked list, we're going to have a private node called head. And then we're going to have our constructor for our linked list. Public linked list is going to take no parameters. This is set head equal to null. Make sense? All right. So that's what a node is right now. That's what a linked list is. Just going to keep my extra pieces over here. So again, look in linked list. The constructor for a linked list just sets head equal to null. So let's go out to driver. We'll go ahead and create ourselves a linked list called LL, and this guy's going to be a new linked list, which is going to call upon our constructor here we just wrote. And what does this guy do? It sets head equal to null. And that's what my linked list is right now. That's its current state. If I print this out, system.out.println LL, it'll give me the memory address of that new object. There's my linked list object. Okay? So right now, my linked list object looks like this. It has a single field, a type node called head, that points to nothing. It's currently equal to null. Now, the whole purpose of linked lists are we should be able to add values to our linked lists. That is, I should be able to create a 2 and add it to my linked list. Does that make sense? So I'm going to need to add a ability to my linked list called add. Public void, let's call this guy add end. He's going to take in a value that we want to add to the end. Okay? If this is currently my linked list, and I call that guy and I say, I want to add the value 2 onto the end of this linked list. What is required for me to add the value 2, the integer 2, into this linked list? So in code, this guy is called LL. This is LL. In order to put 2 into this linked list, I must first make it a node. I need to wrap this inside of a node, right? 2 needs to become the payload of a brand new node object. So I'll go ahead and I'm going to say node n is equal to new node value. What's that going to do? It's going to call upon our nodes constructor, this guy, pass it value in as payload. It'll set that node's payload equal to whatever I passed it, and then set his next node equal to nothing. Okay? So this one line of code here, what did that do? It created this guy. It created a node whose payload is 2, whose next node points to null. Now, how do I add this node to my linked list? Well, if I'm adding it to the end of my linked list, I need to walk all the way to the end of my linked list. But in our simple case right now, we know where the beginning of my linked list is, right? We also know that there currently isn't anything in our linked list. So what do I need to do? I need to make head point to this guy. Does that make sense? So if head is currently equal to null, That is, if we're dealing with the empty linked list, I need to make head point to my new node I just created. Now, to kind of put this into context, earlier I talked about a pointer counter. What did I call this guy? I called him N. Right now I have a variable named N that points to this node, right? So this node's pointer count is currently 1. This guy lives somewhere in memory. Now we're going to ask a question. We're going to say if head is equal to null. That is, if this is currently the empty list, we're going to make it the 1 list. So we're going to say head is equal to N. What does that do? It takes head, which is currently null, and points it at whatever N points to, which then makes the pointer count here 2. 2 different things point to that guy. And here, if we're trying to keep this very accurate, N is a pointer which points to this node in memory. So there are 2 things pointing at this node. That's why the pointer count is 2. Okay? And that's the end of the method as of right now. When we hit the end of this method, the addEnd method, what happens to this variable, N? This was a local variable to this method, right? Its scope lived and died with this method. So at the end of this method, what happens to N?
It's not taking up memory.
It disappears. It's going to be released from memory. So at the end of that method, N goes away. It died with that method, which then makes the pointer count drop to 1. Can we automatic garbage collect this guy? Nope, because it's still not 0. So we're good. And this is something that's important for us to understand. In older languages, even in Java, but specifically in older languages, if you didn't pay attention to your local variables versus global variables, you potentially could have a piece of memory get garbage collected when you didn't intend for it to get garbage collected. Okay? So you always must make sure that you have at least one thing pointing to all objects that you don't want to lose to keep that pointer count at least at 1. All right? So that's what happens right now. Inside of addEnd. Actually, just for the sake of argument, let me call this one addFront. We'll do that one. We'll do the easy one first. I'm just trying to figure out where our good breaking point will be around 8 o'clock. The code in here is not going to change. I just changed the name of it for right now because we haven't done the interesting part that would make it different yet. Okay? If head is null, we're going to set head equal to N. But what if head is not null? That is, what if I'm adding 5 to the front of this list? So let's say my list currently looks like this. Okay? And then I call addFront. I pass in a 5. What's the very first thing we do? We create a brand new node called N with our 5. What does that do? It creates this guy. That is a node whose payload is 5 and whose next node points to null. That's what our node constructor says to do. Set the payload to whatever was passed in, set next node to nothing. Okay? Now, I want to add this guy onto the front of this list. That is to say, I want head to point here, I want this guy to point here, and I want this guy to continue to point to null. So I want to insert the 5 before the 2 in my list. How would I do that? Well, I got to be careful. Right off the bat. If I immediately just say, oh, well, I want head to point to that guy.
Then you have nothing.
What did I just do?
It'll be 0, and there'll be nothing.
I just killed off the rest of my list. In this case, we only have one guy, but let's say we have a list of 1,000 things, and I'm adding one dude in front of them. By setting head to point to my new node, I literally just cut off all communication to the whole rest of the list. Nothing currently points there, and the whole list will become garbage collected. Don't want to do that. Okay? So the very first thing we do should not be change what head points to. Why? Because we need to preserve access to this guy. Ultimately, what's going to happen? We want this guy to point to the same thing that head points to. So we want this guy's next node to be the same as head. That's where we need to add an ability to node. Set next node. It's going to take a node as a parameter, and we're going to say this dot next node is equal to n. Whatever node we pass in. Okay? By default, all nodes have a next node that's nothing, that's null. All right? So right now, we just built the fresh new node that is 5. His next node defaults to null. That's what the constructor says to do. But then, what do we want to do? We want to set this guy's next node to point to the same thing head points to, which will make that count go up to 2. Does that make sense? So inside of linked list, if I'm in this else, that means not the empty list. This guy means I am the empty list. So make head point to me. If I'm not the empty list, I need to. So insert n before all other nodes. Make sense? So inside this else, what we'll say is we're going to say n dot set next node. To what? We want n to point to the exact same place that head points to. So we want n's next node to be equal to the memory address that head is equal to. So they both point to the same place. Does that make sense? Then we want head to point to n. Which drops that down to a 1. Understand how the order there is very important? So make sure we update the new node first, then make head point to the new node. Okay, so that's what our list will look like right now. Well, that's what it would look like if we did this. Inside driver, if I create my linked list, and I say ll.add front 2, then ll.add front 5.
It's 1-1.
I'm always testing you. So the 5 should come before the 2, because the order we added it, right? Now we'll go ahead and run this, and our program has no output. It got stored. My program doesn't display anything. So we probably want to teach a linked list how to display itself, right? So if this is my linked list, and I'm going to display it, if head is null, that means I have the empty list, correct? That's the easy way to display a linked list. So I'll come into linked list. We're going to write a method here, public void display. And we'll say if head is equal to null, system.out.println empty list. Okay. If I don't add anything to my list here, and I just say ll.display, it'll display empty list. I created a brand new linked list. The brand new linked list did what? It said head equal to null. That's all it does. Then I told it to display itself. It asked the question if head is null, print out empty list. So there is my empty list. But now I want to add some crap to this guy, and then I want to still be able to display it. So my display needs to get a little bit more complex. Else, not the empty list. So we want to go through, and we probably want to have our linked list display something like this. Maybe we have it display a 5, followed by an arrow, followed by a 2. Maybe that's what it looks like. Okay? Showing us the links in the linked list. So in order to do that, we need to display whatever's at the beginning of the list. A couple different ways we can do this. Well, I want this guy to be able to tell me his payload. Because that's really what I displayed here, right? The 5 is this guy's payload. So we need to go back into our node, and we need to add the ability public int get payload. And he'll return the payload. So I should be able to go to head and say, give me your payload, and get my 5. That make sense? Then, how do I get to here? After I've gotten this guy's payload, I need to get to the next part of my list. In order to get from here to here, I need to get this guy's next node. That make sense? We can set a next node, but we currently do not know how to get a next node. So I'm going to add another method here, public node get next node. And we'll have that guy return the next node. So we've just taught our node object a couple of magic tricks. We taught him how to give us access to its private field payload. We taught him how to give us access to its private field node, get node, or private field next node. And then we also gave us write access to his next node, so we could set it. Okay? So what we want to do, we do not want to change the value of head. So we can't make head point to here, then head point to here, then head point to someplace else, because then we'll break head. So we're going to need to have a temporary variable. Maybe we call this cur node. And maybe initially, cur node points to the same thing that head points to. Okay? So we're going to go ahead and say node cur node is equal to head. So they're both pointing to the same place. Then we'll say we want to keep displaying stuff as long as what's true. As long as cur node is pointing to something real. Because initially cur node will be pointing here. Then we're going to do what we're going to do. Then we're going to say cur node is equal to cur node's next node. So cur node will be pointing here. As long as that's not null, display this guy's payload. Then we'll say cur node is equal to cur node's next node, which will be null. And we're going to be done displaying stuff then. So we're going to say while cur node is not equal to null. As long as we have a real node that we're looking at, we're going to say system.out.print. We won't kick it down a line yet. We'll just say print. And what are we going to print? We're going to print kernode.getPayload, followed by an arrow. Okay, and a space. Then we're going to say kernode is equal to kernode.getNextNode. So we'll initially start kernode off at the front of the list at head. As long as kernode is not currently equal to null, we'll print kernode get payload, we'll print as payload, then a little arrow, then we'll change kernode to whatever kernode's next node is. Spin back up, do this again and again and again until we finally hit a kernode that is equal to null. That is to say, kernode will start here. We'll print this guy's payload followed by an arrow. Then we'll set kernode's next node. Well, then we'll set kernode equal to kernode's next node. That makes some point here. Then again, we'll print out 2 followed by an arrow. Then we'll set kernode equal to kernode's next node, which will point to null. Then we'll notice, oh, he's currently pointing to null. So maybe in the final output, maybe we say null. That's the end of the list or something like that. So this is our endpoint. So when we're done with our while loop here, we'll just do a little system.out.println null to say we're at the end. And that also kicks it down a line with the println. Okay, so that's what display does. Okay, let's see this in action. So we'll go ahead and display our empty list. Then we will add a 2 and display it. Then we'll add a 5 and display it. So we should see empty list, then the list that is 2 pointing to null, then the list that is 5 pointing to 2 pointing to null. That make sense?
But it's not printed. Oh, it's at the end. No. Okay.
Yep, the null was our way of here at the very end.
Yeah.
It's our println.
Yeah.
So what do we have left up here? We have one little trailing arrow, and then we just printed out null at the end and said that's the end of the list. Points to null. Okay? So that's adding things to the front of the list, which is the easy way of doing things. Okay? Now, what should be interesting here so far is we're building a generic data structure, our first data structure, which is a linked list. We're building this guy generically so that we can have it hold values and we can build our list, just like we did with our elastic array. The elastic array was horribly inefficient, but hey, it held numbers, right? Who cares if it took up 17 gigabytes to hold 100,000 numbers in? Snooze, you lose. That's why we have memory. Buy more, right? But we're writing this generically. So right now we're able to add things to the front of the list. Well, we're then going to want to be able to add things to the end of the list. And that's where we see our first problem with linked lists. To add something to the end of an array, let's just assume that you had a 1,000 bucket array, but there's currently only 10 things in there. So you don't have to build a brand new array. So buckets 0 through 9 are currently being taken up. And you want to add something to bucket 10. You just go to bucket 10, put the new something there, and you're done, right? Not so with linked lists. With linked lists, we have to, if we want to add something to the end of the linked list, we have to literally walk from the beginning of our linked list all the way to the end of our linked list. How do we know we're at the end of our linked list? When we finally get to a node whose next node is null. That make sense? Okay, so let's take about a 10-minute break. We'll come back at 7 after, and I'll get the first half uploaded here. I got to create the YouTube channel and stuff for this. And then we'll do an add end when we come back. And then the real nightmare comes in when we add somewhere in the middle. And then what about removing crap? All right. See everybody in 10 minutes.